So we've got a number of topics to begin with. We're talking about material for chapter 7. And that means, of course, that we're going to look at homework problems. I'm going to start with the homework problems that were asked because those form a framework for the lecture, and B, that'll make sure that I answer the questions that were asked without going off on tangents with regard to more generalized material. So let's make sure that I have the generalized material down. So we want to talk free energy. And yours was spontaneity with regard to temperature, I think? Yeah. Okay. Were there any other topics that were mentioned that I should have just written down? Does that cover it so far? Okay. If another topic occurs to you, please let me know. Okay. All right. So we'll start with the questions first. So question 54 from chapter 7. For this reaction, the reaction of carbon monoxide with oxygen gas forming CO2. This is what type of reaction, first of all? This is a specific type of reaction, isn't it? What are we seeing here to these substances? There we go. Okay, so yeah, what type of reaction are we seeing? I would say this is a synthesis reaction. Yeah, we're taking carbon monoxide and diatomic oxygen, and we're ending up with CO2. So we're synthesizing CO2, if you will. Does that make sense to you guys so far? Okay. Now this wants to talk about equilibrium concentrations at a certain temperature. So we were talking about equilibrium. We're talking about K. How comfortable are you guys with the idea of equilibrium? If I asked you a question saying, what is the definition of equilibrium? What would you tell me? What is the definition of equilibrium? Okay, see? Good. All right, that's good. That's one of the reasons why I start with these questions to begin with, is because when you start looking at these questions and I start asking kind of more broad questions, meta questions, if you can't answer the nebulous question, then that's important because the concepts are still key to comprehension. Okay, so what we are talking about here is equilibrium. And even before we talk about equilibrium, we got to go further back and talk about, so this is chapter 7, right? Equilibrium is pretty far into the topic of chapter 7. It's toward the end of chapter 7. There is a lot of stuff in chapter 7, right? So are you guys comfortable with heat changes, with exothermic and endothermic ideas with regard to enthalpy, the general idea of heat? Anyone concerned or confused about exothermic versus endothermic? If I said, what is an exothermic reaction, what would you say? Releasing. Yeah. So if you're having trouble with this, does anyone know what exo, the exo means external, outside, exiting, like the word exit, or exoskeleton? Okay, so exo means outside, external, so on and so forth, versus endo, meaning inside, internal. Now, of course, there are some very classic examples of this. What is an endoskeleton versus an exoskeleton? Precisely. We have an endoskeleton. Exactly. We have an internal skeleton versus an external skeleton. Precisely. And I like to mention those here because those are things that you can actually think about. I saw a really creepy TikTok video last night. This girl was shaking her hand and she goes, I got a shake. And then she has a voice that says to her, oh, that's just your skeleton preparing to hatch. That's creepy. Anyways, thought I'd add that to that as well. Now you're creeped out. It's not even Halloween. It's fantastic. Okay, so with exo and endo then, exothermic means energy becomes external, because thermic basically means heat. Okay, thermic, thermal gloves. Thermic means heat. So exothermic means external heat or exiting heat, released heat. So energy becomes external, which of course means what we have to do is we should really look at an energy diagram. I don't think I've talked energy diagrams with you guys. Has the book talked energy diagrams? I always forget if this book talks energy diagrams. The general idea of an energy diagram would be, this would be enthalpy on the y-axis, and typically kind of you could say something like time on the x-axis. And for a reaction of something going like A reactant to B product, if the energy of the bonds, so this is A, and if the energy of the bonds in A is higher than the energy of the bonds in B, then you end up with something like this with regard to time. Now, if you were to actually look at the energetics of the reaction, it wouldn't go straight down. What always happens actually is the reaction reaches a highest energy level, a highest energy point first. Has this been something you guys saw in the book at all, or in any of the videos I showed? I think some of the videos showed this. I tried to pick ones that did, because this is important. The energy goes up first and then comes back down. And in the conversation in the monologue I had in Tuesday, I relate this to the idea of breaking pencils. Okay, you can imagine that before you start trying to break the pencil, you don't put any energy into it. It's stable. So that's kind of where we are right here. This is the pencil at stable ground. Now, breaking pencils is not a downhill process typically, but you actually have to start putting energy into it, pressing onto it physically. So putting energy into the breaking of the pencil, right? And right before the pencil breaks is when you can feel yourself making the greatest effort to break it, right? You have to put the most energy into it right before it breaks. So the point right before it breaks, or that point between broken and not broken, is what we would call, the name for this point, that highest energy point, is the transition state. And what that is the highest energy point between product and reactant. Okay, and that's important because if there was no transition state to begin with, then all downhill reactions like this, and this is what we call a downhill reaction because the energy of the bonds in A are higher than the energy of the bonds in B. So because of that, the movement from A to B releases energy. Okay, the energy difference between A and B, look at the energy difference right here. So energy difference between A and B, this right here, what do you think this is actually? If we were to talk about what sort of actual enthalpy is, this is delta H, and specifically, it is a very specific one. This is the delta H of the reaction. That energy difference between A and B on here is the delta H of the reaction. That is the energy difference between the energy that is in the bonds of A and in the bonds of B. Or really, I should say, that is required to break the bonds of A and required to break the bonds of B. Okay. That is delta H of the reaction. The energy difference between the energy of the products and the energy of the reactants. Okay. There's also an energy difference right here between the transition state, for example, and the reactants. And this right here has another name. This is called the activation energy. And specifically, that's the energy, activation energy of a forward reaction. We'll come back to the idea of a reverse reaction in a moment. But let's assume that this is only a forward reaction, a reaction that is irreversible. Not all reactions are reversible. An irreversible reaction. There's an activation energy, an energy required to reach the transition state. Okay. Activation energy is additional energy required to reach the transition state. So the activation energy affects the spontaneity of a reaction, because the larger the activation energy, the harder it is for a reaction to occur. The smaller the activation energy, the easier it is for it. That should make sense. Okay. If it takes a lot of energy to climb a hill before you can go back down, that's gonna make fewer people climb that hill. Or another way to think about it is, where does that energy come from to be able to overcome that activation energy? Well, that comes from a few places. The energy to overcome activation energy can come from thermal heat, surroundings. But actually what that means is thermal heat is actually just surrounding energy. So that can be a part of overcoming the activation energy. What happens in a chemical reaction is chemical reactions, especially if you're doing like something like A plus B to become C plus D, if you have something like this where there's more than one thing involved in the reaction, they will involve typically actual physical crashes of the molecules. The specific term associated with this would be collisions. Okay, so molecular collisions are what is responsible for these things occurring. And there is energy that is released when these things collide. Okay. Collisions provide energy. For the chemical reaction. And then there is also something that can slow down a reaction. Reactions can be slowed by the correct versus incorrect collision occurring. Not all collisions are guaranteed to be productive, okay? And without going into a lot of detail about that, let's just say that what's going on there is, for example, if we have a reaction like the one we're talking about here, the carbon monoxide plus O2 giving us CO2, something to think about with regard to that is you've actually got these collisions to occur correctly, or you won't get product made. So if carbon monoxide looks something like this, and diatomic oxygen looks like this, then if the collision occurs on the side of carbon monoxide with the oxygen facing the oxygens, there's not going to be a reaction. You've got to get the oxygen to strike on the side where the carbon is facing the other oxygen on the diatomic oxygen to actually get the production of CO2. Another way to think about this is you can't hook up a trailer to a truck on the front of the truck. You have to hook these things up correctly to make them function. Okay? And it doesn't matter how hard you strike those two oxygens together, one on the carbon monoxide and the other one on the oxygen molecule, it's not going to cause it to link up to the other carbon. Okay? So you have to have these things attached correctly. And so statistically, you can think about it as these are ineffective or failed collisions versus successful collisions. And the lower the percentage of successful collisions that will exist, depending upon the shape of these molecules and what we're actually talking about, the sort of chemistry we're trying to do, the larger the activation energy. Okay, so if there's a low percentage of molecular collisions that will result in a successful reaction, you're going to have a high activation energy. You're going to have a very large hill to climb before you get to go back down toward whatever you're trying to achieve. And, you know, if it's a non-spontaneous reaction, you're climbing uphill to go uphill. You guys following me so far? We're doing okay? All right. So I don't want to spend a lot of time on this, but these are things that are important to understand because these are big concepts that can affect the world in a very large way. We're talking about, though, what causes a reaction to be spontaneous. Now we're talking about activation energy. And if we're talking about activation energy, then activation energy can affect how frequently even a spontaneous reaction can occur. And in fact, that's precisely true. Activation energy is what determines essentially determines the rate of a reaction. So reaction rate is determined by the size of the activation energy. And it should make sense to you that activation energy will always be positive. You will always have to overcome activation energy. You will always have to put energy into the system to make it over the activation energy. There is no such thing as a negative activation energy. That's not a thing. No, that's a terrible color. We do not want to start drawing that. I don't even know why they make it an option. So all activation energies are positive, and therefore rate limiting. The larger the activation energy, the less frequent the reaction, and therefore the slower the reaction. Okay? The reaction is going to be slower the larger the activation energy is, because it requires that much more energy to be put into the reaction every time it happens. You must make that investment that much more of an investment. A great example of this is, it's essentially, you can think about it as, and it's a common analogy, it's an energy tax. You have to pay this energy tax or this energy fee before you can actually do the reaction. And so the higher or larger the energy tax or the larger the energy fee, the less number of times or the less often per time you'll be able to do this reaction, because you'll have less raw energy available to do the reaction. Okay. Does that make sense, guys? You with me so far? Okay. Now, a reason you should be grateful that activation energies exist is because activation energies are the only thing standing between you and spontaneous human combustion. We are flammable. We are. Yeah. Reality is the human body is flammable. Okay. And so therefore, be grateful that activation energies exist, because otherwise you would just burst into flames. Good so far? Okay. On that depressing note, well, actually, an uplifting note, because it won't happen. Activation energies will always exist unless someone rewrites the fundamental laws of physics. Activation energies will always exist. So that's an uplifting note. Okay, so we're talking about things that limit rates. Why are we talking about things that limit rates? Well, to begin with, I know I'm going to need more slides. One thing, we're talking about rates because this chapter involves rates. Yes, that's true. This is one of the topics of the chapter. It goes beyond that, though. One of the things you can use, we don't really do this at all in this class, unfortunately, but there's just not enough time to. You can spend an entire semester or even part of semester just talking about reaction rates and the actual equations that go into modeling the reaction rate. And why that is so important is reaction rates can actually tell you what reaction is occurring. Because when you start to actually study chemical reactions in detail, there are different possible reactions that could occur. You might have one reaction that looks like it could occur, but if you look at it in more detail, there are multiple ways of having the reaction occur. And so therefore, coming up with how the reaction is occurring and therefore determining it mathematically allows you to substantially prove what chemistry is actually occurring. And that matters because the more detail we have to understanding an actual reaction, we have the ability to modify or affect that reaction. That is how we determine how to create medications to target specific aspects of things that are occurring in your body. We start to try to understand the reactions that are going on inside the body, and therefore, with that understanding, we can then try to design a more effective medication. Okay? All of that aside, okay, we're talking about big things here that are started from small places, understanding reaction rate, things like that. It also matters for another reason, which we'll talk about in a second. Now, before we come to that, not all reactions are reversible, but some reactions are. Okay? Some reactions can be reversed. If you fry an egg, can you take that egg and unfry it? Not to my knowledge. If you take a piece of paper and you burn it and it's got writing on it, you can't collect all the molecules, recreate a piece of paper, and have that piece of paper still have all the writing on it. Even if you could recreate the piece of paper, which is theoretically possible if you would collect all the carbon and carbon dioxide and other things that are produced from it, collect it back, have some sort of mechanism for reconstructing a piece of paper from it. Even if you could do that, you still wouldn't be able to recreate the writing on it. So that reaction technically would not be reversed. You'd have a new piece of paper that you had built from the molecules of the previous piece of paper. There are a lot of chemical reactions that are not reversible, but there are also other ones that are reversible. Those reversible reactions are ones that we make use of all the time. Reversible reactions exist inside every single rechargeable battery, for example. Any sort of rechargeable battery utilizes a reversible reaction. So therefore, charging your cell phone is a reversible reaction. Charging any battery that is rechargeable is a reversible reaction. For all intents and purposes, alkaline batteries are not rechargeable and therefore are an example of an irreversible reaction. Okay. Reversible reactions mean that when written, there is a forward reaction and a reverse reaction. Okay. There's a forward reaction and a reverse reaction. This is actually something I've been wanting to look up. So here, apparently my computer's not very happy right now. Okay, that's fine too. Let's just look at this very briefly. I have a huge problem with leaving a question unanswered. Here it is. There it is. Okay, so come on. Okay, fine. Where did it go? There. Okay. There it is. So looking at this, here's your reaction. If you add I2, you're adding a reactant, it shifts to the right. Okay. If H2 is removed, you are pulling on it, you shift to the left. A catalyst is added, nothing happens. Exactly. Nothing changes. The temperature is increased. Look at delta H. Delta H is negative. This is an exothermic reaction. If temperature is increased, it shifts to the left. Okay. Because this guy right here means you've got H2 plus I2, equilibrium of HI plus delta H. Okay. Make sense, guys? All right, awesome. No problem. And yes, I wanted to take the time to explain all this to you guys because this is, to me, honestly, this stuff is easy when once you can process it and get through it. But it's the process of getting through it that's difficult.
Yeah, I gotta say, man, just that like initial learning curve, looking at these things is so much harder than when it like clicks.
Yes.
You know what I mean?